Okay, so thanks for coming to this next video. In this section, we're going to continue with some of our analog uh, computation, and specifically today, we're going to show how to make a polynomial function generator. So while the analog computer is used to solve differential equations, it can also be used to generate functions, and we're going to need as we get to more complicated problems, we're going to need to be able to generate our own functions. So we can imagine, like we went over in the previous video, we have these circuit elements that will integrate a signal. So if we can imagine just passing in a single, constant voltage, then the output is going to be the integral from 0 to, some integration time later times the signal we put in, and then dt. And remember, the negative here is really just a artifact of the integration circuit. So kind of if we opened up the black box of this integration block, we would it would make sense. We'd be able to show why do we have this negative, and we'll do that in the future. But for now, just remember that any signal we pass in to the integrator, we get the integral, and then we get this extra negative sign in front. And of course, if we integrate just a constant value, we're going to get t plus some, uh, you know, uh, constant. Now, the solution to the integral has to be equal to, at time 0, has to be equal to the initial condition. So remember, we're also going to feed in an initial condition. And if we were to feed in just the initial condition of 0, then of course t plus c at time 0 is just going to be, that's just going to leave our constant. And if our initial condition is equal to 0, then c is equal to 0. And then what we're going to do is we can just keep passing this signal in through subsequent integrators to get higher order polynomials. So if we pass this into another integrator, forgive the crappy drawing here, we're going to get again the negative of the integral of our signal, which was negative t to begin with, again from 0 to t dt. So we can we can integrate this. The negative is going to cancel, and we'll get 1/2 t squared plus, again, some constant. So again, if we set the initial condition to 0, then this constant will just be 0. And then we can just keep on doing this. So right here, we've just, have a pretty simple way of generating this polynomial series. So that's what we are going to do. So quickly, what I'll do now is I'll just show how to program this, and then we'll look at the results on the oscilloscope. Okay, so here we can see this is a finished patch, a finished program for the analog computer. And I'll go over, we're going to do it, I'll take it apart and kind of go step by step. But the main thing to see here is first, starting just with this initial signal down here, this is going to be our, let's see here in the corner, this right here is just going to be our +1 that we're going to feed into our series of integrations at the top. So as we pass this signal through the series of integrations, we will generate higher order polynomials. Yeah. So let's go ahead and just take it apart here. So I'll leave the black colors for measurements for our oscilloscope. And right now we're just going to, if I adjust this, you can see here's our power coming in, just the power of the computer, and then here's our X and our Y oscilloscope readings, which if we want to read signals on these X and Ys, we have to connect the signal to these output jacks down here. I'm going to go and push it forward just so you can see it a little bit better. Okay, so we start with +1, and I'm going to go ahead and pass it through the coefficient, just that way I can scale it up and down kind of as I choose. So this will pass the +1 into our first, let's see here. Yeah, it'll pass it into our first integrator. And then if I want to integrate it further, I take the output and again, run it into the next input. So this will go from 1 to x squared, x cubed, so on and so forth. So for now, we'll do these 4 integrations here, or these 3 integrations, I think is enough. And then of course, we need to set each initial condition. So for now, I'll just put a +1. But most of these initial conditions, I'll show you what happens when we shift the initial condition, but a lot of these we'll just be setting to 0. Let's see here. Here's our IC. here. Okay. So now each integration has a initial condition, and then now we need to go ahead and put in our measurement signals. But remember, because this one is going to be a minus x, because the integral always gives the negative, I'll go ahead and invert this one before we pass it into x. For this next one, we don't need to do that because the negative cancels out, so we can go directly into y. And then for z, we will go ahead and invert it again. Okay. All right, and there we go. So I'll go ahead and set the coefficients to 0 here, and I'll pull back our op time. So remember, the op time down here is just the how far forward we're going to integrate it. And something that we're going to really want to pay attention to, and I'll show on the oscilloscope in a second, but this OL, which stands for overload. And the thing to remember with the analog computer is that it can only represent to you know, a certain machine voltage. It can't keep going higher and higher voltage. So as if you integrate x from 0 to infinity, the x will approach infinity. So obviously the voltage will go higher than what the machine can handle, and that's what we'll see by this OL. So we don't want to run our op time past that point. But I'll show what it looks like here now on the on the oscilloscope. All right. So all right. So keep in mind, so these first three here, and let me get the oscilloscope to catch. So this little Y bar here, this little Y signal is my trigger. So once the signal passes, it'll go ahead and catch that. And then we have our three sort of additional condition knobs here. And we have our, we're basically scaling. This first coefficient is going to scale what we're feeding into the integrator. So it's kind of like the initial slope of the problem. And what I want to kind of pay attention, like I was saying earlier, is if we go ahead and dial back the op time, this red light right here starts to disappear. And that's important. Like I said, once you integrate the solution forward far enough, eventually it hits that 10-volt rail that you can't actually, the machine, the analog computer can't represent past that. So if I dial, if I kind of decrease the intensity of the signal that I'm passing in, we can go ahead and run the op a little bit farther. But this is really important because we see here kind of the characteristic behavior of these polynomials. The lower order polynomial, which is the line, doesn't, at the very beginning, actually rises faster than the quadratic, but then eventually the quadratic overtakes it. And we'll see that for each, each successfully higher degree polynomial. Further, if I go ahead and switch the oscilloscope now that the second signal is actually going to read the polynomial, we can see, or excuse me, the third order polynomial, we can see that it's an even further delay in the point that the linear line, that the linear signal takes over. And now I can compare the second order versus the third order here. And again, we see the same sort of thing. Now we can also we can adjust these slightly with our other like I said, we on the pen and paper we showed what happens when you set the initial condition to 0. But if you set the if you put the first initial condition not 0, that's adding in an extra term that you're integrating each time. So it's actually going to change the order of the polynomial here. Okay. Yeah, so that's pretty much what I wanted to show here. Just to recap, we passed a signal, a constant signal through these integrators, and this allowed us to generate a polynomial function, and we could continue to do that by, passing it through higher integration steps. And furthermore, there's no feedback here, so we're not solving a differential equation yet. We're just using the electric components to generate these functions. But what we'll show in future videos is we can get these by adding in feedback. We can solve the different differential equations, and we could also generate. What we can recognize is that the solution to the differential equation are themselves functions. So if we want to generate something like a sine or a cosine, we can do that just by wiring this up correctly. Okay, thank you very much for listening.